All right, welcome to our second example. So this is going to be the fourth and final video. So this one we are going to be doing number 57. Again, I'd like you to pause the video, go through, draw your free body diagram, and think about how would you go through and solve this particular question. Okay, so for this one, our free body diagram is going to be a little bit different. We still have our force due to gravity pointing straight down. Here we are being given a force that is pushing on the box. So there are a couple different ways that people like to put this force. I will leave it up to you as to which one you use. Technically, you are supposed to put it from the middle pushing outwards. You could leave it at the corner. I would not fault you for that. We need, I like to also make sure I label my angle so I remember what it is. So I have gravity, I have the force I'm pushing with, and because I am up against a surface, I have a normal force as well. It is, again, normal force has to be perpendicular to the surface, so it can't be up or down. It has to be left or right. The surface is going to be pushing to the right on the box because the box is being stopped from continuing moving to the left. Now again, I'm not done yet. I do need my coordinate system, and I need to think about friction because here I have an issue. My box wants to move down. So that means that I could, if I have static friction, it would point upwards, right? Because it wants to oppose motion. If I have kinetic friction, again, it wants to oppose motion, but I don't know, is my object moving up or down? I don't know which one of these is friction because I don't know the direction my box is moving. So in the case of if you do not know the direction your object is moving and you need friction, it's better just to not include it. Because again, what I've noticed for students is if they include something on the free body diagram, they automatically assume that is correct, and they might apply friction incorrectly because they've guessed the wrong direction initially. So we don't know the direction this box is moving. Therefore, we don't know the direction of friction. Because if the box is going to move upwards, well, that would mean that kinetic friction points down. The box moves down, kinetic friction points down. If the box isn't moving, well, is it not moving, but it would go up if there was no friction, or is it not moving and it would go down if there's no friction? So I don't know. I don't know which direction the friction should point. So I'm just not technically going to include it on my free body diagram. So this question is kind of, but not really similar to the last one. So here we are trying to figure out if the box is initially at rest, are we going to move up, down, or stay at rest for this particular force? So what we're trying to do is figure out is if F is large enough, we move up. If the force is too small, it moves down. So I need to figure out, well, first off, can I overcome static friction? If yes, which direction is my object going to move? So overcoming static friction. If yes, what way do we move? And that would be answered by if the force is large enough or small enough. So let's think about how we would go through and do this. Well, again, if I want to overcome static friction, I need the equation for static friction. If I do that, I'm going to need the normal force. So let's go ahead, go through and figure out what is the normal force. All right, so let's go through and think about what we need. All right, so the force of static friction max is mu s n. I have mu s, I gave that to you, it was 0.5. I need the normal force, and in order to calculate the normal force in this case, I'm going to need my x direction. So again, we're going to start at the top, work our way around. My mysterious frictional force, if I have it, is going to be in the y direction, so I don't need to include it here. My normal force is pointing in positive x, so I'm going to add that. Gravity is in y, can ignore that. I have minus the force I am pushing with, but not all of it. Only some part of that force is in the x direction. The rest of it is in the y direction. So I need to make sure I am using the correct amount of that pushing force. So I need to have force cosine theta. And in this case, my object is just going to be moving up or down the wall, which is my y direction. So that means I have Newton's first law in this case. So again, I'm not moving in my x direction as I'm moving up and down the wall. So when I calculate the normal force, it's going to be normal force is equal to the force I'm pushing with, cosine theta. Again, I don't want to do numbers here to figure out what's happening. So I want to think about two things at the same time. And this is kind of this is where this particular question gets difficult. Let's think about the net force in the y direction. Well, we have plus or minus some type of friction. I don't know if it's up, I don't know if it's down, I don't know if it's static or kinetic. Right? I don't know what type of friction I have. So I'm just going to put it here. I'm going to leave it in red for right now. I'm going to have minus the force due to gravity because it points downwards, plus the push force, but, and I'm pushing it upwards. Again, not the entirety of the force, only part of it. So I have sine theta. And again, is this equal to 0 or is this equal to ma? I don't know which one I have. Right? So I have two major unknowns right now happening in this question. I don't know if I need to add or subtract. Sorry, I guess I have three. I don't know if I need to add or subtract friction. I don't know what type of friction I have. And if I knew what type of friction I had, and I knew the direction of motion, I would be able to figure out if I have 0 or ma. Or if I knew if I was accelerating, I could maybe figure out the other two. So I don't have enough information yet. So what I need to do is look at friction and the other forces separately. So if my static friction is greater than the force due to gravity plus the pushing force, the maximum, didn't give myself quite space to refill that in. So if the maximum static force is larger than the other two, my net force in the y direction is equal to 0. If that's not true, so if our static friction force is less than the force due to gravity plus the push force sine theta, then I have my object accelerating. And the direction it accelerates is going to be dependent on if the force due to gravity or the force of friction is, the force due to gravity or the push force is stronger. So I need to kind of separate the two and solve them separately. So I need to solve for the maximum static friction value and the other force's value and see if they are strong enough to overcome static friction. If they are, then I'm going to be able to find out my direction of my acceleration. If they're not, my object's not moving and I'm done. So let's go ahead and let's solve for that. So let's solve for the maximum value of my static friction. So that's going to be mu s n, where again, normal force in this case is my push force cosine theta. So here my normal force is not at all related to the force due to gravity. Not at all. They're perpendicular to each other. One's in x and one is in y. So again, do not just automatically assume that the normal force is mg or even related to mg. So I have all my values. I have 0.5 times the 12 newtons we can push with, cosine 30 degrees. When I plug this in, I got 5.196 newtons. So this is the value I would need to be at the maximum static friction force. The second I'm at 5.9 or 197 newtons, I start moving. So I need to now know what is negative force due to gravity plus force sine theta. Because again, I'm trying to figure out, do these two forces together overcome static friction? If yes, I'm moving. If no, I'm stationary. So I can rewrite this. I'm going to have minus mg plus my force sine theta. Again, I have all of this. The box is given as 1 kilogram in the image. Assuming I'm on Earth because there's a person in my question. Plus 12 newtons sine 30. When I took this and plugged it in, I got minus 3.4 newtons. So there's a couple of things we have now. One, we know that the static friction maxes out at 1.596 newtons. We know that the other two forces combined is 3.4 newtons downwards. That means that the static friction is going to point up, and it is static friction that is going to be keeping our box in place. So if we wanted to, we could go back into our free body diagram and say that, hey, we have static friction pointing upwards. We now know that we have static friction as our friction. We know it's going to point upwards because our object wants to move downwards because the force due to gravity is stronger than the force we are pushing with. But because we have not overcome the static frictional force, our box will stay at rest. So for this question, it's more complicated than the previous one because we had to make sure that we were overcoming two forces, which we had to calculate separately. With the previous one, we were just given the force we had to overcome. This one is more complicated, and this is probably going to be the most vague question you'll be seeing about forces. Typically, as we move forward into chapter 7, it's a lot clearer which direction the object is going to move in, so we don't need to worry about figuring out the direction as much. All right, so that's going to wrap it up for today's lecture. Please make sure to take the lecture quiz if you haven't already, and if you have any questions, let me know.